And we're back. Not making the trig joke. No, it's not happening. No, I'm not doing it. Okay, thank you, Sage, thank you. Anyway, no. So today we are going to be diving into radians and central angles and things like that. So just like the last lesson, we do have to begin with visual and verbal vocabulary. Less so much the visual, more on the verbal. First of all, what is a central angle? A central angle is any angle who has its vertex at the center of a circle. Boom. Hopefully you all know from geometry that a piece of the circumference of a circle is called an arc. Hopefully you remember that terminology. A piece of a circle is called an arc. And if you can remember from geometry, you have the ability to find the measure of an arc as well as the length of an arc. They're two completely different things. When you have a central angle whose rays go through the edge of the circle, the arc that it creates is called an intercepted arc. It's the portion of a circle whose endpoints are on the sides of a central angle of the circle and whose remaining points lie in the interior of the circle. Essentially, this is an intercepted arc. Question for those of you that were not in my Algebra 2 Honors class. If you were, don't answer. Why do circles have 360 degrees in them? Ooh, I got a brave volunteer, Cooper.
Base 6.
Why base 6? What? Well, it's not a base 6 number, but I see what you're getting at. It's a multiple of 60, but why? Why do we say 360? Oh, Sage is going to lose his mind. Sage?
Because there's 4 right angles that are on 90 degrees.
But why is a right angle 90 degrees? He's trying to, but why is there 180 degrees in half of a circle? You're using circular logic here. Get it to circle. Yeah, Graham?
Isn't it the same reason clocks have 12?
Well, no, but I will tell you that there is a reason why we said there's 12 on a clock.
Is it like a sundial?
No, not even the sundials. No, I mean, You know why you're having okay, Ellie, last chance. No, it's not the pi thing. Here's what it is. The reason why circles have 360 degrees in them is because we said so. That's legitimately the only reason why. Now, Cooper, you were close. I think it was the Mayans, maybe? The Mayans, they used a base 60 number system. Mayans or Aztecs, one of the two. But the real reason why we chose 360 degrees, why we chose the number 360, is literally because 360 can be divided by a lot of things without getting decimals. That's why. You can divide 360 by 1, 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, 18, 20, so on at 24, I think, so on and so forth. It is subdivisible by a lot of things. That's the only reason why we said there's 360 degrees in a circle. So if you went to another planet and you met another intelligent species and you tried to say 360 degrees, you would look short-bust. Okay? No. That would be very strange if they did. That would be very strange if they did. But I will tell you this. It's because that is a human creation. But you know what's not a human creation? It would be something that is part of the very nature of a circle. And that would be a radian. They're part of the very nature of a circle. They were not created by humans. They were literally discovered by humans. All we did was give them a name. And that name is based on the word radius. So, can we agree from center to edge of a circle is a radius? Yes, great. Can we agree that all arcs could be straightened out and then measured to get a length? Yes, great. If you have a central angle, and by the way, all central angles are made up of 2 radiuses. If you have a central angle that creates an arc that has a length that is equal to the length of the radius, you have something that we call a radian, because it's created by a radius, so to speak. Now take this radius slash arc, that is a length of radius, and stack it on itself over and over and over again. And what the ancients found out, I don't know which ancients, but what they found out was, regardless of the size of the circle, regardless of the length of the radius, there were always just a little bit more than 6 of those objects that would fit around a circle. It's actually, to be more accurate, a little bit more than 6 1/4 of them Actually, to be a little bit more accurate than that, it's a little bit more than 6.28 of them. The number 6.28 and change kept coming up over and over and over and over and over again. So they gave it a name. Tau. Tau is the symbol that it's the Greek letter for 2 pi. And half of tau is pi. So as it turns out, there are 2 pi of these objects that will fit around this circle. Again, pi is a number, so if you say 2 pi of something, you're saying a little bit more than 6.28 of them fits around this circle. Regardless of the size of the circle, there's always 2 pi radians, 2 pi of this angle within the circle, always. And if you're curious to know what the size of this angle is in degrees, because you're not used to thinking in radians yet, it's a little bit more than 57 degrees. It's a little bit more than 57. Do you need to know that? No. But it's the kind of thing that's nice to know, because it would be great if you kind of had a feeling for the size of 2 pi over 3 radians, or the size of pi over 5 radians. It'd just be nice if you had a general idea. You know what I'm saying? Kind of like how when we were talking about our logarithms, do I know what log base 2 of 7 equals? No, but I do know it's a little bit less than 3, you know? Because log base 2 of 8 would have been 3. Yes, Sage?
So if that arc is bigger, how it just...
If the arc, it can't be bigger if it's created by this kind of angle. When you say bigger, do you mean longer?
Okay, what if the angle is bigger then?
Well, then it's not a radian anymore. A radian is a set size. This is the size of a radian. Okay? Yes? Yeah, a radian is a set size of something. And there's always 6.28-ish of this angle that will fit inside a circle. Cooper? Okay. So you could say that 2 pi radians is equal to 360 degrees. Of course, you could divide both sides of this by 2 and say that pi radians is 180 degrees. Go with that? Awesome. Going to do a little bit of dimensional analysis here, also known as unit conversion. If you would like to convert from degrees to radians, meaning you already had degrees, then this is what you would need to multiply by. You multiply by pi radians over 180 degrees. Because this fraction equals 1. Pi radians divided by 180 degrees is 1. They're the same measurement. It's like saying 12 inches, 1 foot. They're the same measurement. But if you had radians that you were trying to convert to degrees, the other way around, well, then you would multiply by the reciprocal of this. If you already have radians and you need degrees, then you multiply by 180 degrees over pi radians. Basically, whatever unit you have and you're trying to get rid of, it goes on the bottom. Whatever unit you're trying to end with, it goes on top. I don't know about you guys, but I'm pretty darn lazy. When I can write less, I will. When I can say less, I will. Because radians are a natural part of circles, they're considered the default measurement style. We will never use degrees unless we see the degree symbol. So if no symbol is written, an angle's automatically in radians. That means I don't have to say radians, ever. All I have to do is not write a degree symbol. If I don't write a degree symbol, it is known that's radians. You guys cool with that idea? Awesome. These 3 examples are doing some unit conversion. It says find the radian measure of a 60-degree angle. Okay, well, if I start with 60 degrees, and I need to end with radians, I need to multiply by a fraction that has radians on top. I'm writing it for now, but I didn't have to write rad. It's a choice. What's going to happen here is the degree symbols cancel out. And you're left with this fraction, 60 pi over 180 radians. But 60 over 180 reduces to 1/3. This leaves me pi over 3 radians. Now remember I told you a minute ago, a radian is somewhere around 57 degrees. Can we agree that this number is a little bit bigger than 57 degrees? Yes, so we can all agree that this is a little bit more than 1 radian. Pi divided by 3 is a little bit more than 1 radian. This is just a much better way of writing it instead of that. Yes, London?
Do we have to know that 1 radian is about 57?
No, you don't need to know that it's about 57. It's kind of like I said with logarithms. I'd like you to be able to think about their size without having to know their exact size. So I know this should be a little bit more than 1. And since I know pi is bigger than 3, I know this is a little bit more than 1, so I trust that I'm right. That's it. It's just to know that, yeah, that seems right. You know what I mean? For example, half of 57 is somewhere around 30, right? So pi over 2 should be close to, with pi over 2 radians. No, I'm saying this wrong. Now I've confused myself. What was I trying to say? Pi over 2 radians, I was doing it way wrong. I was saying if you had about 30 degrees, you'd have about a half of a radian. Well, that means you would need a number that was about half of this. So like a sixth of it, maybe pi over 6. It's just things like that. It's just thinking about generalized sizes. You don't have to know it. It just helps. Okay. 85 degrees. Same idea. We're going to start with degrees. If I'm trying to move over to radians, that means I need radians on top. And you know what? I'm tired of writing rad. I don't want to write it anymore. I don't need to. It's not necessary. The degree symbols will cancel. And if you were trying to do this without a calculator, you would have to just give me a reduced fraction. The only number I know that goes in both of those numbers is 5. And it's like 17 pi over 36. I'll be real with you, I have no idea what that is. Like if you ask me what's the generalized size of 17 pi over 36, I'm like, I don't know. I'm not really sure. I know that it's almost 18 pi over 36, which is almost half of a pi. But even pi radians, and since pi radians is 180 degrees, it's like close to 90 degrees, something like that. How about we get an actual, out of curiosity, how about we get this in an actual decimal? 17, here's pi. So it's this many radians, about 1.484 radians. So 57 times this number-ish degrees. I know it's a little bit less than 90. Do you have to know that? No. But that's how I like to think about it. This last one, converting radians to degrees. Well, I've got 2.5 radians, and if I'm trying to get rid, I don't even have to write rad. I don't have to. If I'm trying to get rid of rads, I need rads on the bottom. That means I need 180 degrees on top. And I have no freaking clue what this number is. So I'm going to grab a calculator. But I can estimate it. What's 2.5 radians? And a radian's almost 60. So 2.5 times 60. Well, 2 times 60 is 120. 0.5 times 60 is 30. So this would be somewhere around 150 degrees-ish. Somewhere around there. Did you need to know that? No, it's just neat if you can think about it. 2.5 times 180 divided by second pi. Again, the pi button is right there. What did I say? Somewhere around 150 degrees. 143.239 degrees. Last time, if you don't see a degree symbol, it is automatically radians. Speaking of, boop, every scientific and graphing calculator has the ability to work in radians or degrees. I keep my calculator in radians. The only time I change it to degrees is if a question is working with degrees. If you would like to know how to change it between degree mode and radian mode, you press the mode button, boop, and scroll down. It's right there, radians and degrees. I keep it in radian mode. More often than not, you're going to work with radians. Yes, that will affect your answers. If your calculator's in the wrong mode, yes. Yes?
Is it on
It'll affect your trigonometry work.
Is it on radian or 43 by default?
I have no idea. It should be on radian by default. Yes?
Why didn't you change it to degrees for the first two?
Because it won't convert between the two for me.
That doesn't make sense.
Why wouldn't it make sense?
Because you just said you change it when you use degree.
When you're doing trigonometry. We're not doing any trig right now. So like say you want to know sine of 60 degrees. I'm currently in degree mode. So it's reading that as 60 degrees. Ready for this? If I put it in radian mode and I type that, it's reading that as sine of 60 radians, which is a completely different answer. So the mode matters when you're doing trigonometry. Now, if you're just dividing things, it's not going to make a difference. Right now, it's not going to affect us, okay? But I wanted to make sure that you saw how to do it. You'll need to swap between the two on assessments, yes. If a question asks you about degrees, then you need to be in degree mode. It's pretty simple. In AP Precalculus, we're going to focus almost primarily on radians. We will use degrees very, very seldomly, okay? That's what it says up there. Okay, now, this is asking us to draw these things. And that is actually kind of difficult without what I'm about to draw on this paper. You don't need to have this drawn. I just need you to understand what I'm drawing and go with me, okay? I'm going to draw an XY axis. I'm going to pretend there's a circle going around it. Pretend you see a circle. Whee! Okay? Can we agree that right here is 0 degrees in standard position? Then what would this be in standard position? 90 degrees. What about this one? 180 degrees. Right here. 270 degrees, and yes, this is also 360 degrees. Okay, but we're not going to use degrees very often. Instead, what we're going to do is we're going to work in radians. And like I said, you don't have to have this drawn. I just need you to see it and understand it. This is 0 radians, but it's also 2 pi radians. 180 degrees is pi radians. Now what we're going to do is we're going to start talking about fractions of pies. I'm going to start treating pi like it's a unit. It's not, but we're going to treat it like one. What's halfway between 0 pies and 1 pi? 1/2 of a pi. 90 degrees is pi over 2 radians. Now we're counting by halves. 1/2, 2/2, 3/2, 4/2. Isn't that neat? 1/2, 2/2, which is 1, 3/2, 4/2, which is 2. Pies. Obviously, all of these have the number pi next to them. I'm being lazy. I'm treating pi like it's a unit. It's not. Okay? Now let me ask you a question. What's halfway between 0 and 1/2? 1/4. Now what's halfway between 0 degrees and 90 degrees? 45 degrees. But you just said that it was 1/4 of a pi. So all of those are 1/4. 1/4, 2/4 reduced, 3/4 of a pi, which is also 135 degrees. Here's 4/4 reduced to 1. Here's 5/4 of a pi. Also 225 degrees. Here's 6/4 reduced. Here's 7/4, which is going to be, what, 315 degrees? And there's 8/4 reduced. So your pi over 4s are quarters of a pi. Look how many quarters there are in a full circle. 8. 1, 2, 3, 4, 5, 6, 7, 8. I sliced the circle into 8 pieces because there are 4 pieces, there are 4/4 in every one. Comfortable with that idea? Awesome. we're going to sketch negative pi over 4 radians. Negative? What makes an angle negative? Clockwise motion, opening the wrong way. That means if this is 0 radians, this is negative pi radians, because I'm going clockwise. That makes this negative pi over 2 radians, and halfway between 0 and negative 1/2 would be negative 1/4. There it is. Now the cool thing about your over 2's is that, well, that's just 2 of these fourths. Or you could just know that 1/2 is halfway between 0 and 1 pi's. But that was easy. That's just right here. That's a 90-degree angle, pi over 2 radians. Time for me to go back to my piece of paper and draw some more. Now I need thirds. This represents 2 pi, 0 and 2 pi, right? I'm not going to even use degrees this time. Maybe I will. This is 0 degrees, 360 degrees. We know that this is pi radians, which is 180 degrees. We know that this is pi over 2 radians, which is 90 degrees. We know that this is 3 pi over 2 radians, which is 270 degrees. There, we've got our full circle on there. Cool? How many thirds, listen to the question, how many thirds are there in one thing? 3 thirds in 1. So this 1 pi can be split into 3 thirds. Here's 1/3 of a pi. Hey, what's 180 degrees divided by 3? 60. 60 degrees. Okay, cool, thanks. So there's 1/3. Here's 2 thirds. And if this was 60 degrees, this is just double that. So it's 120 degrees. By the way, here's 3 pi over 3, reduced. Here's 4 thirds. So it's 60 times 4, because that's a 60, and this is times 4, so that's 240 degrees. Here's 5 thirds. That's 60 times 5, or 300 degrees. Here's 6 thirds reduced. There are, ignore the black, 1, 2, 3, well, here. Now you can ignore the black. 1, 2, 3, 4, 5, 6 slices. I've cut that circle into 6 slices. Cool with that idea? There's 2 pi over 3. So how would you draw it without knowing this? Here's how I think about it. Remember, I'm cheating, and I'm thinking about these pi's as units. They're not, but that's how I'm thinking about it. Is 2 over 3 bigger than or smaller than 1/2? Bigger than 1/2 guarantees you that you're going past that. Is 2 thirds bigger than or smaller than 1? Smaller than 1, guaranteeing that you're going to be before that. Guaranteed you're in quadrant 2. So knowing what quadrant you're in is extremely important in trigonometry. Now we're just going to, do our best to draw something that is 2 thirds the distance from 0 to here. And that's going to be about there-ish. Something like that. That's 2 pi over 3. Great. And I'm a little disappointed in these notes, because you know what delineation, demarcation, fraction of pi I don't see on here that is important? Sixths. So I'm going to come back to this image that I drew in blue, and I'm going to ask you, What's halfway between 0 and 1/3? 1/6. Of course, half of 60 degrees is 30 degrees. 1/6, 2/6 reduced, 3/6 reduced, 4/6 reduced, 5/6. Well, if that's 30 degrees, this is also 30 degrees. 30 degrees before 180 degrees, 150 degrees. 6/6 reduced. 7/6. It's 30 degrees after this, 210 degrees. 8/6 reduced. 9/6 reduced. 10/6 reduced. 11/6. It's kind of struggling to see all these words. And if this is 30 degrees after 0, this is 30 degrees before 360 degrees, that's 330 degrees. Look how many red slices there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Why? Because there are 12 sixths in 2. So yeah, the notes are a little disappointing because they don't have any representation of the 1 pi over 6 triangles, slices. So I've got my pi over 4 slices, my blue pi over 6 slices, blue pi over 3 slices, excuse me, red pi over 6 slices. Notice that there were 4 unique green ones, 4 unique blue ones, 4 unique red ones. Isn't that interesting? Because I know there's 12 red ones, but half of them are reducible. The other half aren't. Right? All right. Let's do some work with it. The minute hand of a clock travels how many radians in 5 minutes? Okay, let me ask you, how many minutes are there around the clock? 60 minutes. Great. And how many times will 5 go into 60? 12. Actually, I have this upside down. If you're doing 5 of the 60, but yeah, it goes in 12 times. There you go. Sorry, I drew it upside down. So can we all agree that 5 of the 60 minutes is actually 1/12 of the circle? Yeah? Cool with that? Well, how many radians are in a full circle? How many radians? 2 pi radians in a full circle. 2 pi radians in a full circle. So if you'd like to know how many radians there are in 1/12, you do 1 over 12 times 2 pi. That gets you 2 pi over 12, which reduces 2 pi over 6 radians. Which is, what's 180 degrees divided by 6? 30. Okay, that's 30 degrees. See, 360 divided by 12 is 30. But it's pi over 6 radians. The faster you can get your brain moving in radians, the better you're going to be at trigonometry. Let go of SOHCAHTOA, transition to XYR. Let go of degrees, transition to radians. That's what you want to do. This one says, what is theta in radians if you know that this is a 45-degree angle? So if this right here is a 45-degree angle, what I would like to do is ask you how many radians 45 degrees is. How about this? How about this? From here to here is how many degrees? 90 degrees, yes. And 90 degrees was how many radians? Let's see. Well, how about this? From here to here was how many radians? Pi radians. So that from here to here is half of that, or pi over 2 radians. And, 45 degrees is half of 90 degrees, is it not? So half of a pi over 2 is a pi over 4. This little red angle has a measure of pi over 4 radians. How many fourths are there in 2 pi's? 8. there are 8 of these things in a full circle. So if one of them is here, how many of them are over here? There's 8 of these in a whole circle. If one is here, what's out here? 7. So this theta is 7 of those pi over 4s. Oh, by the way, it's also, this angle right here is also negative pi over 4. And what is 2 pi plus negative pi over 4? Well, that's the same thing as 2 pi minus pi over 4. Oh, it's 7 pi over 4. Okay? Last question on this page. Think back to your geometry days. How many degrees are there in a straight line? 180 degrees. Oh, how many radians did we say is 180 degrees? 1 pi radians. Remember, 0, pi, 2 pi. So 180 degrees is pi radians. That tells me these two angles add up to pi radians. 5x plus x equals pi. This gets me 6x equals pi. I'll just divide both sides by 6, and I find out that x has a size of pi over 6. Theta is 5 times that. So that's just 5 pi over 6. There. Or you could think of this as being 6 pi over 6, and I'm 1 before that. 5 pi over 6. Ta-da! And if you wanted to do it in degrees, you could. What's 180 degrees divided by 6? 30 degrees. And what's 30 degrees times 5? 150 degrees. That's 30 degrees. That's 150 degrees. But we're going to do it in radians because that's what we're supposed to do. The unit circle. There are 2 schools of thought on the unit circle. Your old school teachers are going to say that in order for students to be successful with trigonometry and the unit circle, they must memorize it. Bah! And I will say, I could barely remember your names. How in the world would I memorize something with all of these data points? By the way, this is missing the spokes and the degrees that are supposed to be on it. Could you imagine? I mean, you've all seen an image of the unit circle. There's so much crap there. I can't memorize that stuff. I simply can't. It's too much. It's too much. So I don't memorize the unit circle. I think it's a total waste of time. Instead, I know how to build the unit circle if I need to. You are never going to be asked, fill out the whole unit circle. Nobody cares. You're going to be asked to use your knowledge of it. So I'll use my knowledge of it instead of knowing the unit circle. I do have to memorize a small amount of stuff. You need to memorize the X, Y, R relationships that I talked about instead of SOHCAHTOA. You need to know X, Y, R. And other than X, Y, R, you need to know these 2 special right triangles that you should have learned in geometry. They are the 30-60-90 triangle and the 45-45-90 triangle. Yes, I'm using degrees as their names and not radians. Why, Mr. M? Because 45-45-90 is much easier to say than pi over 4, pi over 4, pi over 2. That's why. It's just less syllables. And 30-60-90 is much easier to say than pi over 6, pi over 3, pi over 2. It just doesn't roll off the tongue like 30-60-90 and 45-45-90 does. Okay? And when I draw these things, and I'll be drawing them a lot, when I draw these things, I always put degrees in them. Why? Because it's easier to fit a number than a fraction. That's legitimately the only reason why I use the degrees instead of the radians, because the fractions are tall and it's hard to fit in the triangle. I want to fill out my 45-45-90 triangle first. If these 2 angles are the same, what does it tell you about this triangle? If it has 2 congruent angles,
That is a right triangle.
that doesn't guarantee right triangle. It guarantees an isosceles triangle. That's what it guarantees. Good. Because I have two congruent angles, I'm guaranteed to have two congruent sides, specifically the ones that are opposite from, across from, the 45-degree angles. These two sides have the same length. These two sides can be any length you want them to be. The author of these notes and a lot of textbooks want you to say, call it x, and call it x. And then if you use the Pythagorean theorem, x squared plus x squared equals this thing squared, and you take the square root of what you're going to get is x root 2. Meaning if this is 7, and that's 7 root 2, whatever. I'm going to use knowledge of this triangle to do trigonometry, which means I'm going to assign a value to x. I'm just going to pick a very easy number for x to be. What's a really easy number for x to be?
-1.
Why would -1 be an easy number? Who in their right mind says pick an easy number and you go -1? This guy.
Quadrant 2.
No, this is in quadrant 1. Anyway, what's a great... He says how? Just like that. Now it's in quadrant 1. See? All right. Anyway, what's a very easy number for x to be? 1. So this side is 1, this side is 1, this side is 1 times root 2 or root 2. I will often call this a 1, 1, root 2 triangle. Remember, these numbers that I've written in green are numbers that I have assigned. This triangle could be any size. It could be 6, 6, 6, root 2. It could be root 2, 2, for all you know. But the point is, the ratio of the side lengths is these two are equal, and this one is always those sides times root 2. So you might as well just go with easy numbers 1, 1, root 2. Memorize that triangle. Next, the 30, 60, 90 triangle. Again, the way the author of these notes and a lot of textbooks want me to do that is this way. The side length across from the 30-degree angle is always the smallest side because it's across from the smallest angle. You could call that x. The hypotenuse is always double that. And the leg across from the 60-degree angle will always be the short leg times the square root of 3. But I don't want to use these x's. I understand that when I draw these triangles, I'm doing it for my own benefit and to memorize the ratios. So I'm going to pick an easy number for x. Not -1, but +1 is a very easy number to choose for x. Because if you do that, this side is 1, the hypotenuse then is double that, and the long leg is instantly root 3. This is a 1 root 3 triangle, 1 root 3 2 triangle, a 30, 60, 90 triangle. And just so you don't get it confused, this triangle could be reoriented, and I'll just squeeze it up here, so that the angle that's in standard position, the one in the bottom left, picture not drawn on the scale, is the 30-degree angle. It doesn't change anything. I'm trying to pick a good color. The side length across from the 30-degree angle will always be the 1. The hypotenuse will always be the 2. The side length across from the 60-degree angle, which has to be that one, is always the root 3. If you know your x, y, r relationships for sine, cosine, and tangent, and you know these actuality 2 triangles, you don't need to memorize the unit circle. You don't need to. Are there any questions on what I've filled out so far? Yes?
Do you have to memorize that?
Yes. You need to know these from geometry and your x, y, r relationships. Or you will need to memorize the unit circle. And that's awful. I only know one person on this campus that has the unit circle memorized. No, it's not me. I don't have it memorized. I don't even know your name. How? Oh, like, what's his name? John or something? Like, you know what I'm saying? Like, I can't memorize a unit circle.
John.
No, that's Cooper. I know what his name is, but my point is, it's so much. It's so much. I don't have it memorized. And I actually called Miss Stinson and I asked her one time, do you have the unit circle memorized? And she was like, no, why would I memorize it when I can build it? I was like, okay, thank you. I asked Miss Bluebaum the same question. Do you have the unit circle memorized? She said, no, why would I would just build it. And I go, thank you. And then I called my best friend down at North Ohio. I said, hey, do you have the unit circle memorized? He's like, no, why would I memorize that when I could just build it? I was like, okay, thank you.
Who has it memorized?
Miss Klein has it memorized.
What does he teach?
She teaches Algebra 2 regular.
And MCA? Yes. Anyway, Ms. Klein is highly intelligent. I'm not trying to memorize that unit circle up. Now, this says find the values of sine, cosine, and tangent at 30 degrees, yada, yada, yada. No, I don't feel like using that. I'm going to do it without that knowledge. This is what we're going to do, and I'm going to finish this regardless of when I hear that bell. Here's how I'm going to do that. Don't you back that up, Cooper. John, get it out of your folder right now. I'm not done. Here we go. I'm going to draw an angle in quadrant 1 at 30 degrees. Picture not drawn to scale because who cares? This is my right triangle. Here is my 30-degree angle. I'm going to fill out the classic ratio side lengths on a 30, 60, 90. There's a 1 across from the 30. The hypotenuse slash radius is 2, and the cross from the 60 will always be a root 3. Now to do some trig. Sine of 30 degrees. Sine uses y over r. My y value is a 1. My radius is a 2. Sine of 30 degrees is 1/2. Cosine of 30 degrees. Cosine is x over r. My x value is root 3. My radius is 2. And lastly, tangent of 30 degrees is y over x. My y is 1. My x is root 3. I did not need a unit circle. I did not need the picture that I covered with my calculator. I did that with a knowledge of special right triangles and my knowledge of the x-y-r ratios. One more important thing that I want to say before I stop the video. This image shows a radius of 1. That makes this a unit circle. Hey, look! This is what I got for cosine of 30 degrees. It's almost like x is cosine of theta. This is what I got for sine of 30 degrees. It's almost like y is sine of theta. How interesting. So interesting. Thank you, nerds. John, now you can pack up, you turd.